So here we are at the Gripen atelier, where we're setting up the production line for the Gemera, but also we have moved into our new engine and transmission area where we by hand assemble and build the transmission and engines for the Jesko and also for the Gemera soon. So please follow along and I'll show you what it's all about. So this is a environmentally controlled atmosphere where we have clean enough air for this kind of procedure, and it's really like Swiss watch manufacturing in a way, but at a larger scale. So we can have a little closer look at some of the components going into the transmission. So we have Robin and his two colleagues here building the transmissions on these stands. One person can build one transmission per week, so it's a relatively convenient process that we have set up. And what we can see here are some of the internals. And many of you wonder how this transmission works, and it's really quite a marvel, I would say, and never seen before technology. So maybe Robin, you can help me here a little bit, explain what we're seeing here.
So the parts that we're seeing is the gears inside of the gearbox.
Right,
actually.
Exactly. With the clutches as well, right?
Yeah, correct. That's the clutches.
So wet clutches,
yep.
Hydraulically controlled.
Yes.
I think it's about 130 bar or something like that, pretty high pressure.
Yep, 130, 140.
Yeah, exactly.
Around there.
So here we have 3 gears and one more. So we have 7 gears.
Yes.
Maybe you can explain a little bit how they work together.
All right. So to select like the first gear, for example, we will activate 2 gear packs. This one for first gear, and that one. And when you switch to second gear, you will activate this one, and still that one. And third will be this one and that one.
Right. So it's always a combination of 2 gears.
Of course, that's
we have 3 shafts, right?
Yep.
So
that's how we managed to get 9 gears out of 6, actually.
Exactly. So most of the shafts have 2 sets of clutches, and one shaft actually has 3 sets of clutches, because one also carries the reverse, I guess. So 7 clutches in total. And I guess, as we can see here, they're organized in this triangular pattern, so they're not lying like this on the table, but it's the easiest way to explain it, really. And this comes together and creates this very, very compact transmission, which includes the starter motor, and you can also say it includes the flywheel and clutch, because there is no outstanding flywheel or clutch like a normal transmission, because we actually only use these clutches also for takeoff. And since we didn't have an outside clutch, we decided not to have a flywheel and simulated to see how the engine behaved without it, and it looked good on the simulation and even better in reality. And for those of you who heard the Jesko rev, it just revs extremely fast because it has so low inertia on the crankshaft due to this transmission design. So the transmission actually makes the engine behave differently, not only from a shifting or gear perspective, but also from a response perspective. And since this also has the starter motor included, it also adds weight to transmissions that you normally don't have in a transmission, which normally sits on the engine. Still, this is only 90 kilos of weight with everything included, including the hydraulic control system. So it's something we're very proud of. And there are some pretty cool components, and maybe Robin, you can also explain a little bit what these things do.
These are the parts that are distributing oil into the high pressure system. For the clutches. And
it's really a work of art. Again, you get the sense of a Swiss watch-like mechanics and a jewelry-like feel and very high precision. And of course we are talking about high rotational speeds of shafts, high pressure, and it needs to have long lifespan with these seals. So it's really something quite unique.
Oh yes.
What is this then?
This is the starter gear, actually. The one that the starter motor attaches to be able to start the engine.
Exactly, and I guess this is the closest to a flywheel we have. It's not much of a flywheel, but it's the biggest diameter rotating metal part. So this is all the flywheel we have, not a lot. So, and again, the casings are very much works of art, I would say, in the way they are engineered and executed. It's just beautiful. piece of machinery. And very lightweight. Okay, thanks Robin.
Thank you.
Let's go and have a look at the engine as well. Again, here we have 3 stations building engines for the Jesko at the moment. This middle section here will be the production for the Gemera. That's still done in the development area at the moment. Again, one operator can build 1 engine per week. So again, quite high speed, I would say. What we can see here is a little bit internals of the Jesko. The beautiful, very lightweight 180-degree crankshaft. The super light forged pistons with ceramic coating, anti-friction side skirts, and an etched Koenigsegg logo on top. We jokingly say that the Koenigsegg shield protects for the combustion pressure. And what's pretty cool is that when you open up an engine after many, many years of operation, you can still see this shield very clearly. There is no wear or tear to these parts. Just a work of art. We have extremely high cylinder pressure as we have a 5-liter engine with up to 1600 horsepower. We have actually the highest cylinder pressure of any production engine in the world. So all of these components, they need to be very light to take the high RPM, but they also need to be very, very strong to cope with the high cylinder pressures and the high G-forces that's spinning at this speed with relative large displacement. So all the components you see look quite different to what you would find in other production engines. We can see here the cylinder head on the inside. We have, for being a 4-valve cylinder head, we have quite a hemispheric combustion chamber to avoid knocking. And this is something we developed over the years to have a perfect kind of low risk for detonation and knocking and coping with extreme cylinder pressures. So it has to do with the thickness of the materials, the shapes, and the interaction between this shape and this shape, and how the crankshaft is positioned to the cylinder heads and kind of the acceleration of the piston to avoid peak pressure but gaining maximum cylinder pressure on average. That's how you get a lot of power. Here we can see a more complete engine. It's very, very compact. Complete with intake and exhaust and everything. It's under 200 kilos for 1600 horsepower, which is by far the most powerful production engine per cylinder volume with worldwide homologation, meaning it's built to comply with all regulations around the world. It's quite an achievement for a small sports car manufacturer to be able to do this. It is possible because we also develop our own engine controllers, our own software. Everything is holistically integrated with the transmission software, everything working together seamlessly to have maximum power, maximum controllability, and also comply with all the regulations. For those of you who've heard the exhaust sound of the Jesko, not only is it fast revving, but it also sounds like a normally aspirated engine, even though it's turbocharged. Perhaps even like a V12, even though it's a V8. It has a very, very unique sound that we find extremely exciting, that we're very happy about. And it's a sound that kind of came about more or less by itself. It's not a tuned sound, it's what the car and engine wants to sound like. And it has to do with the Inconel titanium exhaust system, it has to do with the camshaft, the combustion chambers, the turbo positions, everything interacting. And I can show you a little bit underneath this heat shroud here what the exhaust system looked like, and it's really a pretty alien looking thing. This is 3D printed Inconel pieces welded together with TIG welding very beautifully by hand. And you can see none of the pipes are round tubes. They're all shapes morphing together to reduce back pressure maximally, but also have as short stretch as possible between the exhaust valves and the turbos to make sure you have response and also good cold start behavior to heat up the catalytic converters. And if you look inside there, you can also see the fantastically well shaped collector also for the wastegate. Really a piece of beauty. And again, this is also 3D printed. This is the thermostat, which is flow optimized to handle the extreme flow capabilities of a 1600 horsepower engine. Again, a work of art. Here we have the intake plenum, which is a combination of carbon fiber top structure and a beautifully casted aluminium underside. 2 throttle bodies, 2 valves per cylinder, capable of taking quite high pressures, coping with the underpressure, overpressure of a boosted system, but still very, very compact. Flow optimized, as you can see from this direction, to spread equally the airflow between all the cylinders. So we're going to show you what this little baby can do in the dyno. So please follow me. So here we are at the Koenigsegg development engine dyno with a production Jesko engine in it. And today we're going to show you what this engine is capable of. First on E85, but then also on E10 95 octane fuel. That's the lowest grade we have here in Europe. It's about the same as 91 octane in the US. We recommend our customers and owners to run on premium fuel, which is 98 in Europe and 93 in the US, but we actually tune the engine on 95 or equivalent of 91 to have a safety margin. It's quite amazing, I mean, how small this engine is, how compact it is. It's only a 5-liter twin turbo, and then we can get 1280 horsepower on 95 octane fuel with catalytic converters, with all the after treatment systems, with circulating crankcase ventilation like you need on a homologated car, and with all the, as I said, after treatment systems. It's really unheard of. No one else that we're aware of is close to that kind of power to weight to size ratio with a very drivable torque range and very tractable engine. So we're very excited today to show you the power band and the output on these different fuels. So let's go into the control room and have a look how this is going to work out. So here we are in the control room of our development dyno in what we call Hangar 3, which is our kind of prototype area for developing the Jesko. And here we have Hassan, who is in charge of tuning and calibrating the engine software, and Abs, who is in charge of running the dyno and making sure the engine is installed correctly and working properly on the dyno. And together with their colleague Rasmus, who's not here today, they have created this amazing result through fine calibration and testing and really pushing the engine through its phases. So I guess it was a difficult task.
Yeah, it was very challenging.
I mean, given how compact and lightweight the engine is, to get all this power out is just unheard of, I guess.
Yeah, these numbers are unbelievable. It's exciting to really work on these on this engine with these boost and torque numbers.
Yeah, and what's the secret? How can it work?
Well, the engine is built to make this power. So
it is.
So that's number one, and then the calibration comes afterwards.
Yeah. And what kind of cylinder pressures are we seeing here?
We usually aim to run around 160 bars of cylinder pressure, so that's quite amazing that the engine is able to withstand that much cylinder pressure.
That's pretty high. But I guess one of the reasons it can withstand 160 bar pressure is because we have quite low peak pressures compared to the kind of base pressure, so we can make use of the pressure. Because peak pressure, you can't really get much power on, it's just damaging the engine, while your average mean pressure is what gives you the power, really. And to make that spread less means you can have a higher average pressure, basically, with less risk.
Exactly.
And there are a lot of reasons why this engine can do that. It has to do with the shape of the combustion engine, it has to do with the camshaft profile, it has to do with the shape of the piston, it has to do with the piston motion at top dead center, and of course the intake tracks and the tuning, the exhaust. There's just so many variables that come together, but also of course control system to really see what's going on. So with the Jesko engine, it's the first time we have ion sensing ignition system, and maybe you can explain a little bit what difference that makes.
So we are basically able to monitor the combustion activity inside the combustion chamber, which is usually not possible unless you have in-cylinder pressure sensors. So by using that, we are able to use any production car, and just by using the ion activity from the spark plugs, we are able to monitor the combustion. So we can monitor misfires, we can monitor knock. So all these things which are important for combustion stability, we can easily monitor that in any production vehicle by using this ion acquisition.
And that means we can get closer to the limit without overstepping the line.
Exactly, and also very precisely for any car, for any series production car, because in development, of course, you can use cylinder pressure sensors, but for series production, you need to have something which can be implemented on any car. So that's why it's very important to have this acquisition system.
Exactly. And what is amazing, I mean, we achieve these incredible power numbers while having an engine which idles well, is tractable, can start in all climates, and is emission proven for the world market. And it's that combination is impossible almost. It's if you have a small engine with a lot of power, usually you don't have very good control over your emissions. But here we have to consider everything, and that's really what makes it so exciting that we can make it work. And then also run on renewable fuel with less CO2 footprint in the form of E85, which also gets more power out of the engine. What's interesting is that we get on 95 octane, meaning low octane, we get 1280 horsepower. And what I understood from our conversation earlier today is that we actually have more leeway on the 95 octane than on E85 at 1600 horsepower. So we're quite conservative at 1280 on 95 octane, which is unbelievable for such a small engine with that power. So maybe one day we can hit like 1 megawatt, we're close to 1 megawatt on 95 octane from a 5-liter engine, which is like completely unheard of. So let's see what these kind of power numbers look and feel like. Let's start with the 85, because I think that's what you have in the tank right now. Okay, let's go.
Let's go.
So the secret to the sauce here really is that we engineer everything from A to Z. Even the engine controller, from electronic circuit board design up to the final part of the software and tuning, including OBD2 and everything, combined that with the fact that we also engineer the entire engine in-house. We really need all those components understood together, worked on by a small team that interacts very closely to really squeeze the maximum potential out of these systems. So that's really the short answer to how this is possible. So that was exciting, 1600 horsepower on E85. So now we've filled up the system with 95 octane and cleaned out the mix of E85 and 95. We're going to run pure 95 E10 European pump gas fuel. Here we will reach around 120 bar instead of 160 bar in cylinder pressure. And as I said before, we still have quite a margin left on 95 octane at 1280 horsepower, which is just insane. So we're not pushing the limit on this, but it's good enough for now. So let's see what it looks like. Here we go. So that was amazing. Almost 1290 horsepower on 95 octane fuel, which is 91 octane in the US, and over 1600 horsepower on E85. We can hear the engine cooling off now. It's crackling in the exhaust. It's just such a beast. But it's a friendly beast. I mean, it's super tractable, it idles nice, it drives smoothly. But when you want the power, it's there for the grabbing. So enjoy, guys. Thank you.